so in this talk, I'll present this challenge of collapsing towers of interpreters and how we've addressed it as a solution in an ideal setting, but hopefully this will have some impact on practice as well, and I'll come back to this. So what is the challenge? So the task is to collapse a tower of interpreters into a one-pass compiler from the high level to the low level, removing all interpretive overhead. So let's look at what a tower of interpreters is abstractly. So here we have one such tower. L0, you can think of it as the lowest level. And then we have an interpreter written in L0 that interprets a language L1. So we go up to L1. And then we have an interpreter written in L1 for a language L2. So we go up a level and so on until we reach the high level Ln. And so the goal is then to derive from this tower of interpreters a one-pass compiler that translates directly from Ln to L0. So you give it an Ln program, and it will compile it into this L0 level. OK, so what would a tower of interpreter look like in the wild? And here is a contrived example, which you can probably piece it together with the things that exist today. So you can imagine having some Python code that is executed to some bytecode that is then executed on an x86 runtime that is emulated in a JavaScript virtual machine on the browser, and eventually it goes to the ARM CPU. So that's just to kind of give you an idea of how things will look like in the wild. Of course, in this talk, I'm not going to show how to collapse this tower in particular, but more in an idealized setting. But here, really, what it would mean is that we would maybe want to have a one-pass compiler that translates directly from Python code to the ARM CPU, or maybe we want to do some partial collapsing, so maybe even going from the Python code to the JavaScript VM it would be nice already, so you can ship optimized code to the browser this way. All right, and so what would a more idealized example look like? So here is one. So you can imagine having a low level, then a tower of evaluators until you reach a high level. And then as a last step, you can think of having a regular expression matcher. And if you think of regular expression as a language, then your matcher is an interpreter for that language of regular expression. And so here, collapsing would mean deriving a one-pass compiler that allows you to compile a regular expression to the low level. And so what would this do is that for a particular regular expression, you create low-level specialized code to match that one regular expression. Here is another example where, say, at the top of your tower, what you have is a modified evaluator. So for example, one where you do additional tracing for debugging, or one where you make the control flow explicit. So say you write this evaluator in continuation passing style. And so now, when you do the collapsing, what you end up doing is transforming from the high level to the low level, and you kind of preserve your modifications in the low level as well. So if you were doing tracing, then you could see that you're also doing tracing at the low level, or if you're doing continuation passing style, then you would actually see that you've basically made all the control flow explicit at the low level. So we will see some instantiation of this. And so these are the examples I've shown. And so in this talk, I will actually show you how to realize the regex and the modified evaluator example. And in general, the idea then is to, from a tower of interpreters, which has all this overhead of like evaluating each level, kind of be able to get to a one-pass compiler. OK. So just to make things more interesting, we will also consider reflective and infinite towers. So I'll get back to that. And to make things a little bit more constrained, for now, for the low-level language, we'll only consider a variant of the lambda calculus, and maybe with some imperative features as well. So think like a scheme-like language. OK, so what does it mean to be a reflective tower of interpreter? So in short, that means that you can, at any level in the tower, you can inspect and modify your program or at runtime. So concretely, the way I've drawn it here is that L0 is the most meta, most low level, if you want. And then Ln is the most user, most object, most high level. And so if you're at one level, you can shift to a different level. So if you're shifting to the meta level, going within your implementation, what you're doing is like you're reifying something that was a program at this level to something that is now data at the meta level. And on the other hand, you can also reflect back. So if you have some data, you can reflect it back as a program, shifting back to the object level. And so just to kind of confuse things a bit, I'm going to completely switch this picture, and I've just like completely flipped it, so that now L0 is actually the most user high level, and Ln is the most meta low level. And I'm doing this because now I want to be able to add as many levels as I want up here. So then the idea now is that you can always shift up a meta level. Conceptually, there's no limit for any language that you're dealing with. You can always ask, well, how is this language implemented? And go back and I mean, go, well, I don't know if you want to go up and down now, but anyway, go up and down the tower and look at these steps as reification and reflection. And so what we mean then is in our setting, we'll consider that you can always go back up and down dynamically, and you can also make any modification, any arbitrary modification at any level. Now the catch is that we are still able to execute such a conceptually infinite tower in finite time, because once we reach a meta level that has no special customizations, we can kind of short circuit into a default semantics. All right. Okay, so just to take it one step at a time, we go back to our finite towers. So here again, I flipped it back the other side. So L0 is the most low level and Ln is the highest level. And so we will do this one-pass compiler. And so first I will give an example in purple, which is inspired by black. And black comes from a long tradition of reflective towers of interpreter, including Brown by Dan Friedman and Mitch Wand, and then Blonde by Olivier Danvy and one of his students. And then black is by Kenichi Asai in Japan. And then so the basic idea of black is that the language at each level is scheme. So here, if you look, this is a valid scheme program. It's just computing Fibonacci. And so I can, at the user level, I can just evaluate this program and run it, like run Fibonacci of 7 and get 13. So that's good. And now, one thing that I can do in both purple and black is some reflection. And this is kind of a fun way to think about these towers of interpreters. In practice, if you were to do reflection, it would be a bit crazy to kind of just mutate the world underneath you as things are running. But this is what we'll be doing here. So EM means execute at meta level. And that means that conceptually we're going one level, we're shifting to the meta level, one level up the tower in this case. And then this code is executed at that level. So here I'm just saying I'm defining a counter to be 0. And then this evalvar is actually referring to some interpreter function. So how do you evaluate variable? And this evalvar is defining that. And so what I'm doing here is that I'm set banging. I'm actually mutating what is the way I evaluate a variable. And so this evalvar takes an expression, an environment, and a continuation. And this is the case for most interpreter function. And here what I'm doing is that if the expression is equal to the symbol n, meaning if I'm evaluating a variable named n, then I increment this counter. And in any case, I do the old evaluation of variable. So basically, by running this code, I've now changed my meta-level interpreter to instrument all variables named n and increment this counter that is defined at the meta level. So if I do Fibonacci of 7, I get the same result as before. And now if I look at the counter at the meta level, I see that it was incremented to reach 102. OK. So now, what about compilation? So one thing we do in purple is that instead of lambda, you can use C lambda to say that this is a compilation unit. And so if I look at the behavior, it's exactly the same as before. I basically have this Fibonacci function, and now I I compiled it, but I'm not showing the target compilation yet. But you can see that it has exactly the same behavior as when this was just a normal lambda. But what's interesting is that I'm claiming that I've compiled this, and I have some modifications at the meta level, this tracing of the variable n, and I can see that it's happening here in the compiled version. So I was compiling with respect to the modified semantics. Okay, and then just to make things clear what's going on, so one thing I can do now is reset eval_var to have the old behavior. And because my fib function was compiled with respect to the tracing semantics, it still does the counter incrementation here. But if I recompile it, doing a new C lambda, then you see that it's actually doing the default behavior again, which is where it's not tracing. Okay, so this was to give an example of what we want to achieve at the end, where we're able to have a way to say, well, compile this lambda, and it will take into account the semantic of the tower at the time compilation happens. And just to give an idea of what the generated code looks like, so I haven't really talked about the target language here, but you can really think that it has like some application, some way of creating cont cells and all this. It has explicit cells for mutation, so we have this counter cell, and then we're explicitly reading the cell and so on. But what's interesting is that even in the generated code, you can see how it collapsed the levels. So in gray, in a slightly lighter font, you have what the original code would look like for Fibonacci in this sort of continuation passing style. And then in black, you have these cell increments. And these cell increments really happen at the meta level, but we've really collapsed everything here. All right, so how are we going to solve the challenge? Well, if we look back at the literature, there's a lot of work on partial evaluation and turning interpreters into compilers. So that's the first step. And so how do these things work? Well, the first Futamura projection says that if you have an interpreter that takes a source program and some input to this program and you get a result, well, you can do it in two steps, where first you specialize the interpreter with respect to the source program, and then you get a target where you can run the input and get the result. So in some sense, by doing this specialization step, what you end up is producing a compiled version of the program. In practice, partial evaluation is tricky to do automatically, especially because you have to do this binding time analysis to figure out, well, should I make this part of, should I execute an expression while doing the specialization, or should I defer it and generate code in the target? So one way around this is to just say, well, we will do the binding time annotation manually, and sort of have this multi-level language. So that's the idea of staging. So then we kind of realize this turning interpreter into a compiler by basically staging the interpreter and kind of sort of manually doing what this mix step does, but doing it in a principled way where all we're doing really is thinking about which parts of our program should be executed during code generation time and which parts should be executed, should create generated code. All right, so the takeaway here is that a staged interpreter yields a compiler. And so just to elaborate a bit on staging, there are multiple ways to realize this. So one is this multi-level language where you explicitly annotate, say, your application or your lambda with a level. And this level would indicate, for example, static and dynamic. So static would mean during code generation time, and dynamic would mean generate code for later. Or you could even have this B could just be some integer, for example. So you would really have a multi-level language with arbitrary number of steps. One approach taken by MetaML is just to use syntax to kind of give you a way to quote as code and then to splice in code. So this should be familiar to people that are used to scheme quotations. And then you have a way to run code as well. And then in Scala, in the lightweight modular staging framework, we do this distinction between code generation time and generated code time by using types. So if you have a type T, then it means execute now during code generation. And if you have a type rep of T, it means generate code to execute later. All right. So in this talk, we will use a little bit a multi-level language as kind of the foundation for our level L0. And then we will use lightweight modular staging as well as a framework to do the language purple that I showed an example of at the beginning. All right, so a stage interpreter yields a compiler. So how can we use this insight to collapse a tower of interpreters? So the first idea would be to just stage each interpreter in the tower. And really what that means is that now we have like a chain of compilers, a tower of compilers, and so we can just compose them to go from ln to L0. But what about the goal of having a one-pass compiler? And this is particularly important for reflection because in reflection we can dynamically jump back and forth between the levels. So if we just had a multi-pass compiler, it would be very hard to be able to realize this jumping back and forth. And furthermore, that means that you really have to stage each one of those interpreters, and if they're different, that means you have some manual work to do, and if they're different languages, you must have like dedicated code generation facility at each of these levels. Okay, so is there another way? So the other key idea is that we will abstract over whether we're generating code or not. So in some sense, we're polymorphic over the stage. And the way we wire this is that we say, well, the base language is this multi-level lambda calculus, which supports stage polymorphism. And by doing this, we can get away by just changing the usermost interpreter. And then the other levels kind of just work in this sort of pass-through mode where they hand down the staging commands, but don't do staging commands of their own. And by doing this, we get a one-pass compiler. So in the rest of the talk, I will kind of show you how to realize this wiring in a few examples, in a few example systems. But just to go back, so if we look at the example towers I showed at the beginning, what it would mean here is that we would only stage the regular expression matcher, or we would only stage the modified evaluator, and then we would get to this picture by relying on the fact that the low level is a stage polymorphic. Okay. So the two systems I will show are pink and purple. And so purple, you've seen an example already, and pink is more of a kind of showing this stage polymorphism from first principle using a multi-level lambda calculus, and purple is using the LMS framework in Scala and polytopic programming via type classes. So one is so pink is a little bit more dynamic, and purple is a little bit more static, because purple is relying on the staging driven by types that is in Scala, and pink is really relying on doing the staging at dynamically by dispatching on whether you have code or not. All right, and then the other one design question is, how do you control the collapse? So in purple, we do this just by having this compilation unit, the C lambda. But we can also do explicit lifting, and it's kind of useful as a proof of concept to do that. So this is what we do in pink. And then the tower size, finite or conceptually infinite, and in each case, you can add reflection and mutation and so on. All right, so let's first look at this multi-level lambda calculus. So the idea then is to have a lift operator to explicitly delay things to generate code. And then we also have this automatic let insertion, which allows us to control the order of operations, make sure we're consistent when we're generating code and not moving side effects around, for example. And then realizing this idea of stage polymorphism. So this multi-level lambda calculus is really like online partial evaluation in the sense that we really dynamically decide the stages of the code. All right, and so we have a few ways of defining the semantics, either as a small step semantic, which is more traditional, or as a definitional interpreter, a big step semantics. And that's nice because we can then really just run it and play with these ideas. So here, I just want to highlight the implementation just to show you that it is something that can be understood, and just highlight how these key ideas of like having a lift operator, stage polymorphism, and let insertion works out. All right, so this is actually pretty much the code in Scala for how you do the multi-stage evaluation. And so one thing that is interesting to see is where the stage polymorphism comes in. So here, when we're evaluating a plus expression, we first evaluate the two sub-expressions, and then we match on the resulting values. And if we have some constants, some numbers, we can directly do the plus operation and return a constant. So this is as if it was executing during the current stage. But if we have two code values, then we actually reflect the plus node for the later stage. And we kind of do this sort of dispatch all through the evaluation. And so for lift, this is the lift operation is kind of similar to what you have in normalization by evaluation, where we kind of go from a value back to an expression. And so say if you have a constant, you just go back to basically this is a constant value and this is a constant expression. And then for a tuple, you just go back to a const pair, for example. And then for a closure, you actually go back to a lambda. So to do this, it's kind of, you have to reify the body of the lambda and so on. And then for the let insertion, what we do, in fact, is just rely on the side effects in the host language so that we can keep track of the operations in the program as it goes on. So when you have a reflect, what you do is that you end up just adding this to a block. And then reify is the part where you kind of accumulate all the reflects that you have within a block. So anyway, this was just to kind of roughly give an idea of how we implement these things, but it's really nothing too special and nothing too fancy. You can do it in Scala and Scheme. You can. It's a small step. So now the question is, how do we use this to actually do collapsing of towers? So the first step is to define a metacircular evaluator that is stage polymorphic. And this is now metacircular, so it's in this language that is not exactly Scheme. It's its own its own thing where lambdas are also take an extra argument for the recursive self, if you want, and then the actual argument. And so if you look at this, what it takes here is that, as usual for an evaluator, you have the expressions that you're evaluating, and then the environment. And in addition here, we just give the eval explicitly to be able to tie the knot. And what's new is this maybe lift, which is really just a way for us to abstract over whether we're lifting or not. So just think of this as maybe this is actually doing the lift operation, or maybe this is just the identity function and not doing anything. And so if we look at where these maybe lifts are, this is where you would, if you were to stage this interpreter, this is where you would put the lifts. So in a sense, you do it for any sort of place where you're returning a value. So if you have a number, then you do this, this maybe lift. If you have a lambda, you return a closure, so you do this maybe lift. If you have a const, you return a pair, so you do this maybe lift, and for quote as well. But for the other cases, you kind of just rely on the stage polymorphism to do the right thing. So here, for plus, we have the two evaluations of the two expressions. And if we end up with two numbers, this plus will be will just execute at the current stage. But if we end up with two code values, this plus will actually create a plus node. So for the elimination form, you kind of just rely on the metacircularity to get the right propagation. And an interesting case is for environments. So here for environments, notice that we don't do any lifting. Well, the idea here is that the environment itself, the structure of the environment, is something you know when you're executing the evaluator. But what you might not know if you're staging the interpreter is the exact values that the variables in the environment are bound to. So if this value turns out to be a code, that means you don't know it. And if it turns out to be a non-code value, that means you know it. So here we again just rely on the fact that we can look up this expression, and depending on what binding we have, we use that. OK, so now that we have this, we can do interpretation. So here I've defined this eval to basically do this, maybe just have the identity function for the maybe lift. And so now it's just an evaluator that is interpreting. And so here I have the source code of factorial, and I can just evaluate this source code and get the right answer. So I'm doing some interpretation. And I can also do double and triple interpretation. This is slowing things down, but it will still give you the right answer. So you can think of this as a mini tower in some sense. OK, so what about compilation? So for compilation, we just use lift as the maybe lift. And now, if I do eval-c of factorial source, I get the code of factorial in a normal form and everything. And so now what I can do is I can witness the collapse by basically doing the wiring as I suggested in the diagram. So we just stage the last interpreter in the tower, and then we always get the same code regardless of how many levels of evaluation we have. So all the overhead of the intermediate level disappears. And so if we go back to this picture, this code kind of realizes this picture where here we had eval-c, and here we had eval-source, eval-source. And so the other thing we can do is do, say, a modified evaluator at the top. And so then we would get some modified code as well. And so here are some examples. So this is the code for the original compilation of the factorial source. So it's just factorial in this sort of with explicit lets for each sub-expression. And then if you do the tracing, you get explicitly those extra log calls. If you do continuation passing style, you get, in addition to the lets, you get an actual explicit lambdas for the continuations. OK. So what about purple? So then in purple, we decided to just use the scheme where we don't have explicit lifting. Everything is just hidden inside this compilation unit of C lambda. And it's really using the lightweight modular staging framework. So compared to pink, it's more like offline partial evaluation, because statically we will kind of try to know whether an expression is in one stage or a second stage, but we can also abstract that over by abstracting over the types. So what we do is that we basically have this type class R of t. Well, we have this type R of t, and if we instantiate R to rep, then we get staging, and if we instantiate R to no rep, where no rep is just defined as no rep t equal t, then we just get interpretation. And if you recall the collapse in purple, then this is kind of the type class we have for the operation. So this is like what the target language looks like. So we have const car coulter, we have explicit cells for explicit mutable cells, and then application, function, continuation, if, and so on. All right, so one thing to notice, though, is that in order to kind of have a reasonable semantic for compiling these reflective towers of interpreter, we do have one difference in terms of the structure of the reflective tower. So if you look at black and also the predecessor, what you have is that kind of each level in the tower has conceptually its own CPU or its own program counter or its own continuation if you want. But in purple, we just have one global CPU, which kind of fits better with this idea that you're going to compile everything down to the same code anyways. And yeah, there are some sort of interesting meta questions about this, because this is not something you can see when you observe each level of the tower. It's really kind of in the meta semantics of the tower that you can notice these differences. OK, and just to recap, so you've seen this earlier example with the modified semantics. What's interesting is that in purple, the levels are not really that clearly delimited when we do this compilation unit anyways. So what's interesting is that even if we define a sort of compiler at the user level, so say if we define a very simple string matcher, then we end up generating code that is actually, that looks like we've compiled that string matcher. So here, for example, if we just want to match whether a string starts with AB, we will actually generate this code where we're explicitly checking, okay, well, is it null? Is the first part of the string A? Is the second part of the string B? And so on. So that's kind of an interesting thing that you can get for free as well. All right, so in summary, what I've shown is how to collapse towers of interpreters. It was some scratch I wanted to itch in some sense, like as an intellectual challenge. And I showed that you could do it in two ways. And the key idea in both is stage polymorphism, so abstracting over whether you're generating code or whether you're executing now. And so I've shown one way to do it in Pink using a stage polymorphic multi-level lambda calculus, and then using the LMS framework and polytopic programming via type classes. And then one design question is how much of this compilation process to expose. So I've shown one extreme where you have explicit stage lifting in Pink, another middle ground where you have the C lambda, where you kind of abstract over the details of staging. And you could go the other extreme, or you can think of maybe using a technology like this in a completely automatic fashion in a JIT, for example, where the JIT would be able to detect that, okay, you could do some like collapsing of towers of interpreters. And so if you did that, you would also have to be very careful about being able to detect that your collapses are out of date with respect to the semantics. And yeah, and this brings, doing JIT would also bring a whole new set of questions about efficiency of the collapsing itself, which is not a given here. So in terms of potential applications, so I guess there are towers in the wild. There are cases where we want to collapse things. I don't claim that this work in this idealized setting can be directly applied there. Maybe it gives some idea of how things could be structured in the wild so that they're more amenable to collapse. One thing where using reflection, where it could be useful, is if you have these sort of modified semantics, then it could be just a nice way to be able to add instrumentation, do various modification on your semantics, but still kind of not pay the price of an interpretation overhead. And finally, non-standard interpretation. So one example I'm particularly interested in is, well, thinking of these sort of more, like here I've only shown towers that are in this sort of functional imperative paradigm. What about like more radical paradigm? So for example, we know that we can have a racket interpreter on top of Minicanren, this relational programming language, and this allows you to basically turn a functional program into a relational program. And Wilbert has a talk tomorrow about all sorts of fun Minicanren stuff. Anyways, so then the question is, what sort of collapsing could we do in that setting? And even in that setting, what's not very clear is what would a staging language look like for a logic programming language. While there has been a lot of work on partial evaluation, for staging it's less clear. And then another idea would be for abstracting abstract machines. So here you're kind of defining an interpreter that you're approximating to do more static analysis sort of work. So can we also use this collapsing approach for this kind of setting, where it's, in general, I suppose one way to put it is that we might not just collapse for performance, but also for like helping in reasoning and being able to do new cases that were not possible before. So thank you, that's all I had. And here are some references, so code for Pink and Purple. If you're curious about reflective towers, there's a long history with brown, blonde, black. You can probably find that. For staging in LMS, I have the website as a good starting point. And for stage polymorphism, Georg Offenberg at ETH did a lot of work on stage polymorphism in the context of high-performance computing, so being able to control the shape of generated code and so on. And so he has some good work on that. So thank you very much.
Thank you. I like your ponies. Questions?
So this strikes me as related to, but in a different field, recursion schemes and fusion of algebras.
Okay.
And sort of your stage polymorphism actually ends up being trying to abstract over like whether you're sort of folding down or back up the tree. Is there any relation there to be explored, or like am I just actually misunderstanding what's going on?
I mean, no. I mean, it sounds related depending on. So then, what would you do with the algebra? So you would control the foldings versus unfoldings, for example, or you would fuse different like algebraic steps into one, or?
Yeah, generally what happens is you fuse the different algebraic steps into one. So, for example, in the Quasar compiler, which is implemented predominantly using recursion schemes, we have a large number of passes that end up getting fused sort of automatically for us.
Okay.
We don't even have to think about it.
Yeah, I mean, I think it's related more to even the sort of staging aspect, right? I mean, you can use staging to do a lot of this sort of fusion as well, and even in a very controlled manner. So you can choose, say, if you wanted to do fusion of these pipelines where you have like map, filter, and things, and so yeah, that's in some sense it sounds like you're doing it using the compilation time of the language, while we're doing it by having a whole phase, like a runtime code generation approach. So you have the whole host language to kind of, control exactly how you want to do the code generation. Does this help, or? Yeah.
I got the feeling that there is an implicit common representation for all the stages that you are trying to collapse.
Yeah, I mean, that's true that in this example, we are relying on this part. So we have the generated code, like the code we generate is really always in this like low-level language. But still, when you have a tower, what happens is that it kind of goes through the other levels that add whatever semantics that is meaningful to them. But I think this is a fair point that we've explored mostly pretty homogeneous towers. But,
yeah, because I was really interested by the practical example. The first example you mentioned, which is basically transforming a Python code to a machine code, say, or whatever. And this means that at each stage you have different representation, which means that each stage should, you have multi-syntax, whatever stage interpretation. I don't know what this means, but
yeah, no, I think that's fair. I think it would require more work to kind of even get something.
Yeah, that's in that case it's.
Yeah, I mean, this would be ideal if you could just stage this Python to bytecode and then get sort of something working. But what's difficult is that it's kind of doing something strange where it's going to this like very low level and then back up.
Yeah,
right?
back up.
And I'm not.
And,
really
and
sure.
in different languages.
Yeah. Yeah, so I think this would be, in any case, like from a research point of view, like if to push this idea further, just to consider more heterogeneous towers where even within the same paradigm, you would consider different languages and even different levels of low level versus high level mixed. I think that's a fair point that I didn't really cover that.
Okay. Yeah.
Thank you, Nada.
All right, thanks.